You're dead in the water, Heather. We cannot copy out here.
I agree. I cannot either.
Okay, good. Yeah, you probably can't hear us.
No, I can hear you now.
Okay.
Oh, that's much better. Yes.
That's much better. Yeah.
Okay,
Yeah,
I think it's my earphones. That's not good.
it's
Right.
talking into your earphones. Okay, I think we're at 55, Heather. So.
Okay, great. So maybe we should get started. So welcome back, everybody. Hope you had a good break, during which I went to a different seminar. So yeah, that's why my earphones have been getting such a workout today. Yeah, so our third and final lecture for this afternoon, or for today, is Professor Lisa Everett from University of Wisconsin-Madison, and she is going to be telling us about quark and lepton flavor physics. So please take it away.
All right. Thank you very much, Heather, and thanks to everybody. I'm sorry I'm not sort of tech savvy enough to have it set up such that you can see me right on the lectures and see my furrowed brow as I try to do so, as I've noticed many of the other lecturers have been able to do. Hopefully we can still sort of connect via this remote format, despite it being very sad that we couldn't all be in Boulder and I could look at mountains, and those of you who like to climb mountains could climb mountains. But in any case, I'd like to start today with basically an overview of standard model and quark and lepton flavor physics, the topic I was assigned. This is a very, very broad, huge topic, and I'm going to try to touch on a number of different things. And we'll see how far we get in these 4 lectures. This is all rather new to me, so I don't have the usual metrics for how long it's going to take to get through what. So let's see how far we get. If you have questions, please let the moderators know in the chat or whatever. And moderators, please feel free to interrupt whenever if I'm missing any questions that are coming from the floor. Okay, so let's start by talking about quarks and leptons of the standard model. And of course, what we know is that these matter particles, they come in 3 copies that differ by their masses. So let's start by just talking about, for example, the up-type quarks. So we have U, C, and T. And then I'm going to write down their quantum numbers with respect to the unbroken symmetries of the standard model, SU3 color and U1 electromagnetism. And of course, the up-type quarks are triplets and have U1 charge plus 2/3. We have also the down-type quarks. So these ones, we also just call them U sub I, where I can run from 1, 2, 3. We also have the down-type. So D, S, and B, otherwise known as D sub I in my notation. Again, triplets, and these ones have charge minus 1/3. We have the charged leptons. U tau. These are the E sub I's. These are obviously singlets under QCD. Have electric charge minus 1. And we have our friends, the neutrinos. Nu1, Nu2, Nu3. Okay, and Nu sub I. Here we have 1 and 0. And I'm going to put a little arrow by these because, as you see, when I talk about, in particular, this first lecture, when we're covering the standard model quark and lepton flavor, I'm going to periodically sort of assume neutrinos are massless and then maybe talk about what happens now that we know that they're really not. Okay, so that's a little, just keep your heads up when I talk about the neutrinos. Now, as we know, within each one of these categories, what we have is these 3 copies are indistinguishable with respect to the unbroken symmetries of the standard model, as I've just written. But of course, they differ in their weak interactions. In particular, in the charge current. And they also differ in terms of their Yukawa interactions with the Higgs sector that are needed to provide mass. In fact, what we know empirically is that the basis in which the weak interactions take a simple form, right? The interactions with the Yukawa interactions with the Higgs take on a more complicated form, and so we have the gauge versus the mass eigenstates. Now, just some terminology here. These are said to have different flavors. So we can talk about quark flavor. Quark flavor is the U sub i's and the D sub i's, right? And then, of course, we also have lepton flavor, I and mu I, right? Within each group, right, of our different types of particles, right, then we have these three copies, which are called the families or the generation. And these, of course, have the same standard model, unbroken standard model of quantum numbers. And so they're the different families or generations. Now, what I wanted to mention this all about is we all know this, but sometimes you'll find we get a little sloppy in various nomenclature around, and one can often use, sorry about that, take care of that. We can sometimes use flavor and family used interchangeably. In particular, sometimes when we mean family, we say flavor. Okay, so just watch for that. I mean, flavor also, obviously, for example, up type and down type are all quark flavors, but different families are only within the up type or within the down type. Okay, so the study of the interactions of these different flavors was crucial to the development of the standard model itself. And as we see, it's also critical in testing the standard model itself as an effective theory, first of all, as a correct description of nature at the energies at which we probed so far, but also on putting very severe and interesting probes on new physics. And so what I would like to do in this sort of huge topic is just some kind of broad brushstrokes topics to cover. So first, we'll just do some sort of intro review of flavor in the standard model. A good place to begin at the beginning. Also good for a Monday, I think. So these are the Yukawa interactions, the charge current, the neutral current, the basic structure of the standard model. You see, flavor in the standard model is actually extraordinarily precise and sort of tightly constrained. And in general, when we try to extend the standard model to include new physics, many of these beautiful, very rigid constraints, which we've seen experimentally seem to hold extraordinarily well, can be just absolutely obliterated. So it provides an incredibly strong constraint on new ideas. I'd like to talk a little bit about the current, I can't spell, I think, current experimental, let's say, situation, meaning we have all kinds of, over the past really 2 decades or more, there's been all kinds of measurements, particularly in the B sector, where we've learned a lot about whether the standard model picture for flavor violation is in fact correct. And there are some interesting tensions in certain parts of the B system as seen. Actually, they've been around for a while, first seen in the B factories by Barr and Bell to some degree, and then now at LHCb and also Bell 2, the next generation B factory. Now, none of these tensions so far are strong enough to indicate discovery, but they've been around at the few sigma, 3 sigma-ish level for quite some time, and they have interesting implications if they hold and if they turn out to be due to new physics rather than some not as well understood as we want theoretical or experimental uncertainty. So I'd like to just have a little bit of a discussion of this, and this is really, I would say, sort of a layperson, meaning I'm really not the expert on these constraints, that there are many people. I'll try to point you to some reviews and other experts who are looking into this, but I think it's important to understand that this is the current situation. Then finally, we'll talk about the implications, and broadly, for new physics. Okay, in particular, this was sometimes called the new physics flavor puzzle. I believe it might have been Yossi Meir who coined that phrase, perhaps. If not, I'm attributing credit to him when someone else said it, but he's also said it many times. The idea being, if there is somehow new physics associated with maybe other problems of the standard model coming in, the energies in reach of the LHC, then the question is, why is order 1 flavor violation very strongly disfavored, actually ruled out in such situations. And then finally, I have a very, again, brief, kind of broad brush situation of theories of standard model, quark and lepton masses and mixings. And this here is what's called the standard model flavor puzzle. In so doing, I'm surely going to rely very heavily on Andre's lectures regarding the neutrino sector and theories of how to get neutrino masses. So let's see how far we can get, okay, with all of this. I have no idea, we'll see. Anyway, we'll try to touch on some of these over the next 4 lectures. Now, I'd like to make a quick note on referencing. It's really impossible to be comprehensive. And so I saw this in a recent talk by Grinstein, and I really liked it. He just said references apologies, meaning undoubtedly we mentioned some and not mention other important things. And so one should not take this as any references I give might just be particular things that I happen to have noticed. They are not meant to provide a overview precise of every contribution of the field. In particular, I'd also like to comment that I won't try to provide sort of historical development chronology. This is another huge, extremely interesting topic that's absolutely worth reading more about. For me, there are certain influences, some of which came from my own experiences at TASI back in 1997 with Heather and Andre and a bunch of other folks. And that would include, so for example, Paul's lectures. More generally, I'm strongly influenced by basically writings on the standard model by Langecker, reviews on flavor physics by Neer, Boras, and many, many others. There's also very excellent recent discussions as of last summer, again at the summer school level, and that was from the SLAC Summer Institute, and this include Altman's-Hopper, Grinstein, Miller, Lumke, and many others who really are expert practitioners, particularly in the area of the implications for the new physics and the tests of the standard model. And they're absolutely the place to go to for more details. Okay. All right. So again, let's see how far we get on with things. Okay. Let's start, as I said at the beginning, with the standard model. As we know, we have the gauge symmetry, SU3 color, SU2 left, U1 hypercharge, which is broken by the Higgs at order 100 GeV. That, all right, U1 electromagnetism, okay. And let's talk about the matter content. I've already sort of covered some of it. Let's just rewrite it in standard model appropriate language. So in the quark sector, we have the doublets QLI. And these have, with respect to the standard model gauge groups 3, 2, 1, 6 hypercharge. And these are, of course, our friends UDL, CSL, TBL, gauge eigenstates. And we have the right-handed objects, which of course, very importantly, are singlets with respect to the SE2 left group. So if you like UR, CR, TR, and we have the DRs. Like so. Okay. Now, for the leptons, here's the lepton doublets, 1, 2, minus 1/2. Okay, we know about these guys. And the charged leptons are these objects, 1, 1, minus 1, and these are the ER and ER. and tau r. And now we get back to our caveat of the neutrinos. Strictly speaking, if we define the standard model operationally, as is often done, to take it to be the situation with this matter content and only renormalizable interactions, then what we have are massless neutrinos. Above matter content. And only renormalizable operators. Okay. Well, then, of course, we can go beyond the standard model to incorporate neutrino masses in a variety of ways, as I'm sure Andre has and will talk about. Okay, so for example, we could introduce, for example, right-handed neutrinos, new RIs, which would be 1, 1, and 0. Okay, or there could be other possibilities. Okay, we don't know at this point whether such right-handed neutrino states exist, or if they do, whether they are part of the low energy theory. Okay, right-handed neutrinos with this particular quantum numbers. So for right now, let's put this aside, and I'll just keep with the standard model operational definition. Okay, and as I said, when we need to bring in the leptons and neutrino masses, we will do so. Note all these above fields are the gauge eigenstates. Okay, so these have a simple gauge interactions we'll discuss in just a moment. They're not the mass eigenstates. And in the typical sort of abuse of notation, what I really should do is sort of label them all. For example, I should take, when I write QLI, I should really write things like QLI 0, for example, and call this one the gauge. Okay, and in typical abuse of notation, mainly because I'm lazy, we're basically not going to do that and assume we know from the context what's happening. Every once in a while I will, but only when it seems important, okay? So just keep a heads up on that. Now, let's talk, now that we have the matter content, let's talk about the standard model interactions. As we know, the standard model Lagrangian, there's the gauge part. So in other words, things like F mu squared, etc. Plus we're going to have the kinetic terms for the fermions. We're going to have the Higgs. And then we're going to have the Yukawa interactions connecting the Higgs to the matter fields. And here I'm going to introduce the Higgs doublet 1, 2, 1/2. This is the usual standard model Higgs sector where we have just one doublet. Okay, and Higgs Lagrangian that looks like the following. H is the usual Higgs potential. And of course, this capital D mu is the covariant derivative. So let's right now talk about, for example, in the kinetic term for the fermions, e.g. for the leptons, right? These things generally look like the following, like psi bar, gamma mu, d mu, right? Okay, so we write out the covariant derivatives in the appropriate way. For example, for the lepton doublets, we have I, L, I bar, gamma mu, d mu plus IG, W mu A, and then our friends the Pauli matrices, minus IG prime over 2 B mu, okay, delta IJ, okay, and then this is L, LJ, okay. So just a reminder here, this G is the weak gauge coupling, G squared over 8 MW squared, is G Fermi over root 2. G prime is the hypercharge coupling, and this thing is not the gut normalized version. Okay, it's the unnormalized one. The taus are the polys, because the lepton doublets are doublets under the SE2 left. And we can write the same thing, type of thing for the right-handed ones, and these guys look like the following: gamma mu, minus I G prime B mu, delta ij, okay, ERJ, okay. And the main important thing here, of course, for all of these things is that what we have here is that these interactions in this gauge eigenstate basis that I'm using, which should really have these little zeros on it, but doesn't, that these are flavor diagonal, meaning they're not connecting different ones of these copies, okay. Furthermore, what we see, if I could also write down the same types of things for the quarks, they're just going to have QCD terms as well. And what we see is we have not only this flavor diagonal aspect, but connected to it, we have basically universality, for example, of the weak interactions. And these things are hardwired into the standard model as we see, right? So this is extremely important. Now let's go to the Yukawas, minus L Yukawa. And I'm going to just define my notation. So here's the uptype. So I'm going to take QL bar. I'm going to take H tilde U R J. So I have I and J here are family indices. And H tilde is just the way we can connect to the upper component of the Higgs. As we will know, we can write the same things for the down type quarks and for the charged leptons. Okay, there we go. And again, I'm not putting in the neutrinos. Notice here I have the left-right convention. So in other words, left is coming in first. So the I in the Yukawa YUIJ is associated with the left and then the right. I'm pointing that out because conventions abound throughout the literature. Many places people flip it. Of course, it doesn't matter. You just have to keep track for when you're defining things properly. And so these YUDE are sort of 3 by 3 arbitrary matrices in family space. Okay. Standard model doesn't give us any clue about what these things actually look like, and theories of what sort of structure they might have would necessarily take us to physics beyond the standard model, as we will get to later on this week. Okay, so now as we know, we can have electroweak symmetry breaking. Right, where the Higgs develops a vacuum expectation value where the V is 246 GeV. And we remember that the mass of the W is GeV over 2. Okay. And furthermore, the Higgs itself, if we write this thing out in unitary gauge, we can write this as the expansion around the minimum of the physical Higgs field H. And therefore, from the Yukawas, we can get the mass matrices MUDE, or just V over root 2, YUDE. And note that the couplings to the physical Higgses, okay, are going to be governed by the exact same structure. Okay, so then in particular, once we diagonalize the mass matrices, the Higgs couplings are also going to be diagonal. That's a feature of the standard model having a single Higgs doublet. Okay. All right, so let's diagonalize these things. Remember, these are arbitrary. And what we want to do is diagonalize them via unitary transformations. And so what we need to do is actually carry out this procedure using what's called biunitary transformation. Okay, so obviously if our fermion mass matrices were Hermitian, we know how to diagonalize that. We can diagonalize that via single unitary transformation. Okay, and so what we do is we do the trick that if we're given some arbitrary MF, where here F can be UD or E, we can then form the Hermitian combinations MF, MF dagger, and MF dagger MF. You can diagonalize these things by the usual means. Okay. And then what we can do is we can write the following: UFL dagger MF UFR MF diagonal. And F here is just U, D, or E. Okay. And of course, this is just the diagonal matrix MF1, MF2, MF3. In general, we're going to order them to have the heaviest one in the third position and the lightest one in the first. Okay, that's just traditional. Okay. And so how do we get these? So again, I can write UFL dagger MF, MF dagger UFL, and that's going to be equal to MF diagonal squared. Okay. Similarly, I can write UFR dagger MF dagger MF UFR equal to the same thing. I'm writing this sort of sloppily as MF squared. Since these combinations are Hermitian, we know that the eigenvalues on this side, these are real and positive. Well, they're real because of Hermitian. They're positive because of the squared form. And we also have the eigenvectors of UFL that constitute UFL and UFR are of course guaranteed to be orthogonal, so we do have unitary transformations. So we can calculate these then by the usual techniques. And then once we substitute, let me just label this equation as a star. So basically calculate UFL, UFR, and then you put into star, making sure you order everybody properly, both of them the same. And then what you have to notice is because of the fact that of the form of this equation star, we're not guaranteed to get basically real and positive eigenvalues out here. And what we want to do is ensure that that happens. So what we can do is we can employ freedom to rephase. So we can perform rephasings in these unitary matrices. There's a tantamount to rephasing our Quark or Lepton fields. Okay, left and right-handed fields. We know we can do this in quantum mechanics, right? So what we usually do is you choose the phases of the UFLs. Okay, basically to put, oops, what did I do? Hold on. I don't know what I did. Oops. Sorry, everybody. Let's try again. Is that better? We back? Let's
Yes.
hope.
We're back.
Thank you. All right, you can tell I am like a supreme novice at this stuff, and it's a skill I never really wanted to have to perfect, but here we are. Okay, so we're going to choose the phases of the left-handed objects, basically to make, eventually they're going to show up in the charge currents. I'm going to make the one and put them into a standard form. Okay, and then after we do that, we still have the situation where we don't have real or positive eigenvalues in the star. Oops, I don't know what is going on. Okay, something is crazy is happening. I'm sorry, everybody. It was going so well for a while there. I don't know what happened. Okay, I'm going to stop and try again. Okay, hold on.
It looked sort of like a button was being held down.
Yeah, but I don't know which one. Okay, all right, let me try it again. I'm ready for anything, I think. Okay, so we're going to choose phases of UR. Okay. To make MF diagonal real and positive. In other words, for UFR, we can write it, for example, as UFR times some diagonal phase matrix, PR. Okay, and that will do the job. Okay. Notice those, of course, don't affect None of these rephasings are going to affect the determination of the NF squareds that we get from the Hermitian combination. Okay. So if I go back and now try to be a little bit more careful about my notation, I can write, for example, UFL is U dagger FL, phi FL 0, where these are now the gauge, and these are the mass. And similarly for okay. So these are the mass eigenstate bases. And now what I can do is I can rewrite the Yukawa ones in the diagonal form. And again, we're going to see that we're going to get just the diagonal objects, and we're going to have the diagonal Higgs couplings as well. So now let's return to the weak interactions, and let's talk about the weak charged current. A minus L weak charge current. So this thing looks like the following: G over root 2, J mu W, W mu minus plus J mu dagger, W mu plus. Okay. Where J mu W is going to equal sign I equals 1 to 3, ELI bar 0. Now I'm going to be careful and put these back in for this critical moment. Okay. So this is again the statement of weak universality. Notice the quarks and the leptons both the same strength in this form. Okay. And of course I can write down the daggered one, let me not bother. And what we can see now is if we go to the mass eigenstate basis, okay. For example, let's look at the term like the following. Okay, let's look at ULI 0, Ckm DLI 0. So that would be just the term in the J mu plus, sorry, J mu dagger W plus over here. Okay, and this one I'm going to then transform it, and we see what we're going to get is UL dagger UDL DL, and this is the thing that's known as the UCKM. That's Kabibo Kobayashi Miskawa. Matrix. We see now that we've gone into the mass eigenstate basis. What we have is now a flavor off diagonal form of the Lagrangian. So let's just write it out for completeness. So we're going to have G over root 2 bar Li gamma mu U dagger CKM IJ ULJ W minus plus ULI CKM DLJ. So this is the Quark parts only. Of course, there's going to be a lepton part. Important thing to notice is this thing is flavor off diagonal. Well, let me put it this way. We've measured it empirically that this UCKM is not equal to the identity matrix. Okay? So therefore, what we see is we have off diagonal interactions that occur via W exchange. Okay. Now notice in the lepton piece, in the absence of neutrino masses, so in the strict operational definition of the standard model, okay, what we can do is, since we're going to have degenerate neutrino states, we can choose to define basically the nu E, nu mu, nu tau as the weak interaction partners of E, mu, tau. Okay, so M nu equals to 0, okay, as strictly speaking it is in the formal definition of the standard model, then and basically define E mu tau as partners of E mu tau. In other words, this is straightforward to say that if everything's degenerate, there's going to be arbitrary rotations and they can't possibly affect physics. Okay. Now, of course, this is not the case in reality. However, the neutrino masses are very, very tiny. right? As we well know, they're basically one electron volt or so. And many experiments are actually not sensitive to them, okay? Some are, of course, neutrino oscillation experiments being the prime example of ones that are. But in the case where they're not, then what we would see is that essentially they can be treated as massless and the lepton mixing is going to drop out, okay? Now, let's just operationally define in case we want to use it later, of course.
Lisa, you've got a couple of questions on the chat.
Oh, good. Okay, let's have it. Let me try to find what I'm doing. Okay, can I go back to the chat window and see what I'm doing? Okay, and I'm trying to figure out how I'm going to do that. Can somebody? Do you mind if somebody reads them out to me? I'm sorry.
Sure.
I know this is
Sure,
ridiculous.
sure. So,
thank you.
May I? Okay. So
Yes.
the first question is, and I'm not sure when this came in, I'm sorry, but what do you mean by universality again?
Oh, yes, universality here just means that for the weak interactions, for example, we're talking about the interactions of the quarks and leptons with the W boson. The coupling strength is just given by the same weak coupling G, right? This is what we mean by this. So then eventually when we go from gauge eigenstate basis to mass eigenstate basis, there are going to be differences depending on the mixings, which is from a different sector. But the main point is that they're all in the gauge eigenstate basis governed by the same coupling strength. It seems like a very straightforward point because it's obviously we've assigned that there's SU2 left is basically the, you know, cross U1 hypercharge, that is the weak interaction, electroweak interactions, right? But the point is it's actually very important later because it has implications for the strengths of various processes for the quark and lepton sector.
Okay, and there's a second question.
Yes.
Okay. In general, there should be diagonal phase matrices in the definition of VCKM, right?
Oh yeah, we're going to get to that. Yeah. So at the end of the day, part of what is going to happen there is that we can employ the same freedom I was talking about. We can employ the freedom in the left-handed rotations because we see the CKN. In fact, I don't know why I stopped the share and I don't really want to do that. So let me try to, am I back? Okay, I think, am I still screen sharing? Sorry about this, everybody.
You're fine. You can
okay,
carry
I'm fine.
on.
Good. Yeah, so the point is that the Ckm matrix itself, we'll talk momentarily about how we parameterize that. Okay, but because ultimately in these expressions we see, we can rotate around the quark fields and we can absorb phases. And so the main point is how many phases of that can we absorb away? And it turns out for 3 generations, there's going to be 1 phase in there that we cannot absorb away. And where we put it is going to be convention dependent. So when you talk about CP violation according to such a phase, you have to talk later about rephasing invariant combinations of quantities, which we'll get to. Okay, any other questions? Shall I go on or?
Carry on.
Okay, thank you. So I was just going to mention for the lepton sector, we can define an analogously with the quarks, we can define the lepton mixing combination that's also going to appear into the charge current. This is known as the Ponte-Corvo-Maki-Sakata matrix, PMNS, and this thing is going to be observable for experiments sensitive to neutrino masses. And obviously is of great importance in the neutrino detection business, as I'm sure Andre has talked about. Okay. All right. So that's the charge current. And where we want to get back to is let's think about the neutral current. So in the neutral current, these are just the couplings, for example, to the photon or the Z-bos on the weak neutral current. And these are all going to be of the following type of form. I R F L I 0 gamma mu, and then okay, I'm just going to decide whether it's the A or the Z or whatever. Okay, FLI 0, and there's going to be the right-handed ones. Okay, So for the electromagnetic interaction, right, this is pure vector, whereas for the weak neutral current, it's part V minus A, like the charge current, but it's also part vector, okay? The vector part is proportional to sine squared theta weak or theta Weinberg. Well, I remember tangent of theta Weinberg is equal to G prime over G in the standard model. Okay. But the important thing for us for this expression is to notice that because here it's the same field in each of these expressions, so basically what happens is because we're doing a unitary transformation to go from the gauge eigenstate basis to the mass eigenstate basis, since it's the same field that enters on both sides, what we're going to get is that because we have U dagger FLR, U dagger FLR is equal to the identity because of it's a unitary transformation, what we have is that these things are still flavor diagonal. So we see in the standard model, in the mass eigenstate basis, basically what we have are flavor diagonal Higgs couplings, flavor diagonal electromagnetic and weak neutral current interactions, but flavor off diagonal weak charge current interactions. And that charge current is defined, the flavor structure of it is governed, CC for charge current, just by our friend the Ckm. As I said, I'm neglecting the leptons at the moment. And in this business, this is such an important matrix, I just call it capital V generally, okay? Now, if one is in the situation where we're in the sort of strict standard model or the experimental domain where we're not sensitive to effects related to neutrino masses, such that lepton mixing is unobservable, for example, in many collider domains, that would be the case. What we have is a separate conservation of E, mu, and tau lepton numbers. So if we compare the quarks, what we have there is we don't have a separate generational number because of the fact that this Ckm matrix has been measured and has off-diagonal entries. Okay. Instead, what we have is a conserved baryon number. Okay. All right. So let's see. Let's talk a little bit now about the masses of the quarks and the leptons. Okay. Leptons are the easiest, so let's start with them. Again, I'm talking about the charged leptons. I'm going to leave the neutrinos out for Andre to discuss. So leptons are the easiest because these are just propagating particles, so we can understand in detail how to measure their masses. These things are hierarchical and they're known extremely well. So for example, the electron mass, 0.510998946 plus or minus, and then we've got 8 zeros here. Okay. Is that A1 or no? I think that's a 3-1, sorry. MEV, and that's, for example, the 2014 code data. All of these values we'll get from the current PDG listings as of 2020. Okay. And mu is also known extremely well. 105 MEV is the sort of thing to keep in your mind. Here's the details. And M tau is much bigger, 1776, and much less well known, as often can be typical for the third generation. Okay, MEV. Now for the quarks, here we have to start being careful because obviously quarks aren't just flying around separately for us to measure them. So what we're talking about here are what are known the current masses for the quarks. In other words, these are the mass parameters that you put in the QCD Lagrangian, and not the constituent masses, for example, that arise from the spontaneous breakdown of chiral symmetry dynamical mass parameters that you get of order 300 MeV. Okay. And since one can't observe bare quarks, how you extract the mass parameter depends in detail on how you define what you're doing and theoretically how you try to extract. And let's just comment, make the rough division between the light quark masses, U, D, and S, and then the heavy, 1C, B, and T, where light versus heavy just has to do with respect to the QCD scale. Okay. Now, light quark masses is a very long story, and I'm not the expert one to tell you all about it. In fact, you've got local experts right there. But let me just comment that in general, with how they're given, would be MQI at some renormalization scale, mu equals 2GeV, and the MS bar scheme is traditional. Okay? And there are many ways to try to extract these things. One can use chiral perturbation theory, lattice, other non-perturbative techniques. I'm just going to give you the values here as of the PDG. So MU, order 2 MeV, MD, double that or so, and MS, significantly larger and more uncertain. There's, in general, better constraints on the combination, the average of MU and MD, or the ratio of the two. Okay? And there's great discussions in the literature in detail about how these extractions are done. As I said, this is a non-trivial process and active research area to be sure to do this properly. It's a very difficult object because these things are obviously, we're dealing with non-perturbative physics. Now for the heavy ones, right? Generally what one's writing, for example, for the C and the B are things of the following form. Some running mass evaluated at a particular scale, taken to be that mass itself in MS bar renormalization scheme. And one can relate this to the pole mass, which is the pole in the propagator. One can have an operational definition for how to do that from QCD. Okay, I'll spare you all the details. These are the quoted values of these running masses. Okay, for the C and the B. And now for the top, another heavy quark, we can actually measure this thing directly. And by we, I mean the good citizens at the Tevatron and LHC. They have done so and are continuing to refine this. And 172.9 plus or minus 0.4 GeV. So what we see is this incredibly hierarchical structure, right? Basically, we have a very light first generation, a medium range second, and a much heavier third generation. And if you plot them out on the log scale, you see relatively equal spacing. You see larger splittings in the up-type quarks and the down-type quarks with the leptons. Okay. But nonetheless, you see we have strong hierarchies for both the quarks and the charged leptons. And that's extremely important. So let's now talk about.
There's another question in the chat.
Yeah,
when you have a second.
please go ahead. Yeah, please go ahead and ask.
Yeah, the question is why is there a bar on the heavy quarks on the M's?
Oh yeah, the bar is because this is generally quoted as a running mass rather than a pole mass as the pole in the propagator. When you have the heavy quarks, you can sort of treat them as opposed to the light quarks where you really have to sort of understand how they're there in the hadrons and figure out how to extract them. With the heavy quarks, you can use things like heavy quark effective theory. And as I said, it is standard to present these in the literature as the running mass, but then you can write, for example, a definition, essentially MQ for some quark, heavy quark mass is basically MQ bar M function of MQ plus, and then there's some order alpha strong corrections, and in fact, there's many details known. So there's a dedicated prescription for how to go from that to what we think the pole mass should be for these quarks. Okay.
Okay, there's one more question. Why do we choose the scale to be 2 GeV for the
Oh,
quark masses?
yes, so that's a good question. I think the best I can answer that is we don't want it to get too close to, basically in the 1 GeV range, we start hitting into where QCD starts becoming very strong, the QCD sort of transition, right? And so, but on the other hand, we're talking about sort of lightest objects, so we don't want to talk about them necessarily at scales much higher than what they are. So it seems to me to be that this was taken to be a sort of reasonable place where you're not too close to sort of the danger zone, but you're kind of as close to it as you can get. And again, I think you have local experts who could probably answer the details of that question far better than I could. But I'm hoping that roughly covers the gist of it.
You are correct.
Thank you. I feel greatly relieved. I would be horrified otherwise. Okay.
It's a convention. It's a convention.
Right, and then people have to decide on the convention, because if everyone picks a different convention, you're going to have to all do the translations, and these are not easy things to do, right?
Well, in fact, there's another convention in the chiral perturbation theory. It's 1 GeV.
Chiral perturbation theory does 1 GeV. Okay, I see.
Yeah, but it's a pain.
Yeah, okay.
Let's move on.
Yes, sounds good. Okay, Lattice expert says, let's sign off on that one right there. Absolutely. Okay, so where we wanted to move on was with the Ckm matrix, which I'm just now going to call V rather than use Ckm, right? Remember, this is a 3x3 unitary. That means this is going to have 9 real parameters. So remember, if you have an arbitrary complex F by F dimensional matrix, you're going to have 2 F squared real parameters. Unitarity, it provides you with F squared constraints. So you have F squared real parameters left over. And now we also have F fields here at 3 ULs and 3 DLs, which each have an arbitrary phase. So what you can do is you can remove, basically, of those 6 fields, you can remove 5 phase differences. You can't remove all 6 because you can't remove the same phase from each, okay? So what we see is we have basically, of our 9 parameters, we can remove 5 from the rephasing of ULDLs, okay? And that's going to give us 4 parameters, and of those 4, 3 are the mixing angles, the rotation angles, if you like. 1 is the CP violating phase, which goes by the name of the Km for Kobayashi-Maskawa phase, okay, for 3 generation standard model. Notice if this was F, this would be F squared, F being the number of families, minus 2F minus 1, F minus 1 squared, and that can be rewritten as F minus 1 over 2, mixing angles, and F minus 1, F minus 2 over 2 phases. So importantly, if you look at this formula, what we know is that if we only had 2 generations, this is the famous result. If F equals 2, there would only be 1 parameter left, and that's just the mixing angle that goes by the name of the Cabibbo angle, and there'd be 0 phases. So we have no CP violation for 2 families only for 3. So this goes back to the earlier question. We write out the V matrix, and let me just write it out in terms of how people generally define the entries. They're generally rewritten as the following. So we have VUD, VUS, VUD, VCD, VCS, VCB, VTD, VTS, VTB. And we can parameterize these. We see it has 4 parameters in there. It can be parameterized a variety of different ways, but here's the standard one. And I'll explain the notation in a second. So we have a rotation in the 2-3 sector, and then we're going to have a rotation in the 1-3 with a phase attached. And then we also have a rotation in the 1-2. And the places where I didn't write anything have zeros in them. So this is what's called the standard parameterization. And it's, of course, not the only thing one can use, but it's standard for a reason, and it's used, for example, in the PDG and many other places. These S's are the sign theta ij is what I'm calling Sij, and similarly cos theta Dij, etc. The delta is equal to the phase parameter delta Ckm. Okay. It's known experimentally that S12 is much larger than S23 is much larger than S13. So we have hierarchical mixing structure where the 1,2 sector is dominant. And in fact, the theta 1,2 is approximately equal to the theta Cabebo, otherwise known as theta C, okay, associated when people talked about 2-generation quark mixing alone in the days before we knew about the 3rd generation. Now, given the hierarchical structure, there's a very interesting and useful way to parameterize the Ckm, and that's the Wolfenstein parameterization. The idea here is that actually, even though the 1,2 mixing is the largest in the quark sector, it's still pretty small. So we can treat that as basically an expansion parameter and write our Ckm as an expansion in this parameter as follows. So keeping terms so that we're unitary up to order lambda to the 4th. So I'm going to write lambda. Notice lambda is in this VUS, so basically associated with 1,2 mixing angle. Okay. Let me just write them all out, and then I'll talk about these entries. So here, lambda is basically, we have 4 real parameters. The lambda is associated with the 1,2 mixing, the sort of theta Cabebo, roughly speaking. And then we also have the 3 other parameters, A, rho, and eta. We can see the eta part is associated with the CP violation. Okay. Now, one will often see the following combinations. Rho bar is rho times 1 minus lambda squared over 2, and eta bar is eta 1 minus lambda squared over 2. Now, the reason why we need to do that is because, of course, here, when we're just sort of remembering it and we're not practitioners, this is sort of good enough, but now people have done, at the level of testing the Ckm picture of flavor violation so strongly that we really need higher order lambda corrections. And there you have to be a little careful because not everybody defines everything in the same way to handle the, basically you can define the lambda as basically as related to Cabebo angle plus subleading effects, and the way the subleading effects are defined can be different depending on different treatments. So one operational definition that I find useful myself, and it's commonplace in literature, is that often one can define lambda to be equal to the VUS entry, period. And then that can give you some way to understand how to calculate the higher order corrections, but just be aware that's not always what people actually do. Okay. Now let's talk about CP violation. See, where am I? I still have a little bit of space. I guess I'll go to the next page. So let's consider, for example, minus VUB star, VUD, VCB star, VCD. Actually, I want to pull this up a little bit so we can see this, right? So remember, these are these various entries here in this matrix, and so we can write out what these things look like. And we see what we get is that this thing is just equal to rho bar plus I eta bar, as I define those things above. Okay, this will be important later when we talk about the CP violation is obviously going to be characterized by having a non-zero value of eta. Okay, but as I commented, it's just traditional to put the CP phase up there in the 1,3 and 3,1 entries. You don't have to do it, and there are many other ways to parameterize the matrix where that's not the case. You're free to rotate that thing around. So what we really want to understand is the invariant measure of CP violation. And that's given by the Yarlskog invariant. J is equal to the imaginary part of VUS, VCB, VUB star, CS star, okay, which equals cos 1, 2, cos 2, 3, cos 1, 3 squared, sine 1, 2, sine 2, 3, sine 1, 3, sine delta. Okay. Now notice I've written it in terms of those particular quantities, but you can write generally imaginary part Vij, Vkl, V star IL, V star Kj, and that's equal to the Yaroscough invariant times some contraction of epsilon tensor, sorry, that's IKM, JLM, okay, like so. And what we can see is if we put the Wolfenstein parameterization forms in there, we see we get this goes like a squared lambda to the 6 times eta bar, okay. And this is important because remember, lambda is a small quantity. Lambda is of order the sine of the Cabibbo angle, which is basically about a 10th. Okay, we actually know this much better than that. Okay, I'm just giving you some squiggle estimates just to get a feel for it. So this is a small object. Notice this is going to be convention independent, right? So when I write my J in that abstract form, I've expressed it both in terms of the PDG parameterization here and also the Wolfenstein here. But I can take other parameterizations. I can calculate J, and I'm going to get the same values, okay? And I put it back in. Notice also, one thing that the PDG convention and any standard one in terms of 3 Euler angle type of combinations tells you is that if any one of the theta ij's is equal to 0, the Yaroscough is equal to 0. So, and that would mean there'd be unobservable CP violation, okay? So this would be representing the fact, for example, in 2 generations, we wouldn't have a 1-3 mixing or 2-3. So there would be zeros there essentially in some limit. And so we'd get vanishing CP violation. Now there's a huge industry, both experimentally and theoretically, directed to measuring these parameters and checking whether the V is unitary. So I'm going to check V unitary. As usual at the end of lectures, I lose my ability to spell properly. Okay. And we want to measure Vij's. Okay. And for some of them, in particular, for some of the absolute values of the entries, there's, as I said, there's been an enormous amount of work over many decades just to measure these things. And some of these things can be measured in a direct way, meaning standard model tree level processes. Okay, so for example, VUD, and again, these are the PDG values, 0.97420 plus or minus 0.00021. Okay, and that one, here's, for example, the type of diagram that you'd have. Okay, so here's an E and a new E. Down here, here's a D going to a U, and then there's going to be the VUD, okay, and there's a W boson. And so, for example, this could be neutron to proton, and then we're going to have the spectator objects, U and D, like so, okay? And that's one way to measure the VUD. So one can do similar kinds of things with other mesons for the VUS. This is a thing related to the lambda, 0.2243 plus or minus 0.0005. And here, for example, a nice diagram for that. I probably won't do this for all of them. And FSU, again, W, E and nu. Okay, so here's a K going to a pi, right? And here's the VUS. So there's a number of these other entries, for example, VCD. You can do the same kinds of things involving D mesons. Okay. By the way, all of these things are going to involve various hadronic uncertainties because we see we're talking about the Quark process. We want to extract information about the underlying Quark processes from interactions from processes involving hadrons. So we have to have all sorts of form factors and other issues that we calculate using non-perturbative techniques, and in particular lattice QCD. Okay. But similarly, we have more direct measurements for VCD, VCB, and VUB. Okay, like so. And again, let me not comment on the details of how one gets these things. This is a whole long, interesting story. Okay. Let's now go talk about the ones we haven't sort of done yet. Right? VTD, VTS. Okay, these are very, very difficult to measure in tree-level processes involving top quarks. So for these, one would rely on indirect measurements, meaning through mixing of the mesons, the BD mesons or the BS mesons. And so here, in the VTD, and VTS. And I left out one of them, which is another direct process, and that's the VTB. In fact, we measure it from single top production, just looking in detail at this vertex, right? And VTB, so not VTB, this right? 1.019 plus or minus 0.025. Alrighty, so then we can make various unitarity checks just based on magnitudes alone. So for example, V dagger V, Ij is delta Ij, that's the test of unitarity, and same with the flip, VV dagger. Diagonal elements of this are going to involve the squares of the absolute value of these parameters, and they're an important test of unitarity. So for example, VUD squared plus VUS squared plus VUB squared is equal to 1. And experimentally, if you put all these things in, and again, this is as of the current PDG, we have 0.9994 plus or minus 0.0005. Okay, so a very strong test of universality. One can also have a similar test, which is not quite as precise, from the VCD squared plus VCS squared plus VCB squared, etc. Okay. So these are ways to check, because remember, we've assumed throughout that we've only have the 3 generations. And if we've somehow missed something, or if this isn't the right theory, then maybe we don't have a unitary V. So it's important to try to measure that, and each entry sort of as individually as possible without relying on unitarity in the extraction itself, so that we can test this empirically. And this is at the level of where people are doing these things at this point. Now, I think we're getting close to the end, but I want to just sort of make a little highlight of the next things to come, and that's the off-diagonal entries of this object. So see, these ones are the diagonal up here. I think I said it, but didn't write it. Oops, didn't want to do that. Okay. Off diagonal, then what we're going to have are various not equal to j, right? Those are going to be equal to 0. And so the most useful one experimentally, there's many of them, right? But one of the most exciting ones is the following: VUD, VUB star plus VCD, VCB star, VTD, VTD star equals to 0. And the reason why is that if we write this condition out and we basically treat each of these terms, they're a complex number, so we can represent them as some vector in the complex plane. It turns out that each of the sides, right, each of these entries here is actually pretty small, but they're all kind of similar order. So what we have is a rather open-looking triangle. So let me try to draw it. So we can draw it like this. I'm terrible artist, so please forgive. And so there's going to be angles. This one's gamma, alpha, theta. This side here is BTD, BTB star. So let's write this like that. And then this one over here would be BCD, BCB star. And then this one over here is VUD, VUB star. Okay. Then we can take this object and we can now rescale it if you like. So let's rescale it so that this side is 1. Okay. So over here we're going to get VTB, VTB star divided by VCD, VCD star. And over here, the same sort of thing, but instead with the ups on the top, PUD, PUD star over VCD, VCD star. Okay, so the area of this triangle, one can calculate it. This area goes like the Yaroscough invariant J over 2, so it's measuring of CP violation. Okay, and when we do this rescaling, if we put in our Wolfenstein parameterization values for these objects, what we see is the following. Let me just write this one down here with the 1 in here again. And I'm going to try to draw it so that it looks sort of the same as what we had before. Let's see. So I'm just going to put some arrows in. This is now -1. We're going backwards. Okay, I'm going to make the coordinates here at the origin 0, 0. Okay, this is going to be 1, 0. Okay. And then up here, you can show are the entries rho bar, eta bar. Okay, so again, here's my angle alpha, beta, and gamma. And we can see, for example, the beta angle is going to be related to VTD, VTB star combination, etc. Okay, and so this thing goes by the name of the Unitary Triangle, even though it's just one of many such triangles. It's the interesting one because, as I said, what we have are rather open, whereas in some of the other combinations, one side just so much dominates that the thing is almost flat. So the hope is to try to measure these things experimentally. Okay, and in fact, yes.
Lisa, there's a bunch of questions.
Good, good. Let's stop and ask questions. I think we're near the time anyway. Yes, please.
Okay. So the first one is that V underscore TS star.
Yes.
Probably when you were writing things down.
Up here.
Where? I think we have to unmute the student, Owen.
Yeah, I probably wrote something wrong down because I do that all the time. It's horrifying.
Okay, well, we're okay.
I think it's the equation right at the bottom of the screen right now. The VTB star, should that be VTS star?
Yeah, because you're talking about the off diagonal ones. So, but you wrote VTB star in the equation, which is a diagonal element in the.
Yeah, that's right. But let's see. No, you mean in this equation, this one here? Is that what you're thinking about? Yes. No, I think. Let's see. Do we have this right?
I think it's correct.
It's correct. But the reason why is because we're talking about going from D to B, right? And then we're summing over the 3 up-type quarks, U, C, and T.
Okay, I see.
Yeah, so I think it's right. I mean, but yeah, thanks. It's good to scrutinize. Yes.
Okay, so
you could write the same kind of thing down. Instead of having D and B, you could have D and S, right? Or you could have B and S, etc. Right?
Okay.
Yeah.
Let's ask another typo question before we come to it. And so we'll drop back. Should that be alpha, beta, and gamma angles? Let's scroll up to where we can see the unitary triangle again.
Yeah, I think it's.
You'll have to scroll up. You're off the screen. Okay, good.
Yeah,
No,
I mean,
down at the bottom. Yeah.
Yes. So the beta one. This is
the bottom picture is fine. The picture at 10 o'clock.
Oh yeah. This is
wrong.
Okay. This is gamma.
Yeah, great.
Thank you. Yes.
Okay. Third question: isn't there a tension now in the determination of VUS from unitarity and from direct measurement?
I believe that is true. I think that part of the issue, if I remember properly, is that in certain for the VUS, I think at the direct. Okay. So let me just kind of try to get the picture straight. The main point is when you do the direct, you get a rather precise result, as we sort of see up here. But there is tension in some of these entries between, for example, I believe it's is it the UB? One of these, there's a tension, for example, between exclusive and inclusive. So there's even an experimental tension. And then there's sort of, as I said, tests of unitarity, and the ones which have a broader error bar, you might sort of extract it. I believe that's true. Let me take a closer look, and maybe I can come back to you next time with a little bit more details on that. But yeah, I think that we're not at the place now where we can sort of verify that every single one of these universality tests or whatever, unitarity tests give you exactly everything perfect. We're not quite there yet, but I think it's pretty close so far. So with sort of, again, devils in some of the details, especially when you start dealing with things like kaons and D mesons and other things where hadronic uncertainties are non-trivial and highly important. Do we have any other classes of questions? Should we stop now?
Have I missed anything, Owen, or there are some more?
Yeah,
So
there's one more.
One other. Yeah. Oh, sorry.
Oh,
Do you want
one
me to do
more
it?
question. Oh, I'll read it.
Okay, go ahead.
It says, so through these scattering processes, we can get these absolute values of the elements, but what about their phases?
Oh yeah, we're going to talk in detail about that next time. Absolutely. In fact, if I scroll down here and we talk about the determination, for example, of the alpha, beta, gamma of these this triangle, et cetera, and like I said, there's other ones. In the standard model, all of these phases would be determined just by the one CKM phase. Okay, so what you tried to do is measure all sorts of processes to determine experimentally or try to verify this triangle, and then you try to over-constrain and see if everything is consistent with the standard model picture. And you might say with the triangle, well, why don't you, instead of trying to measure CP asymmetries, which would give you the alpha, beta, gamma, and to give you the triangle, why don't you try to measure, if you could measure all three sides very precisely, then you can get it that way, just by sort of having to line it up, right? And the answer is it turns out to be much harder to measure the sides to the required precision compared to actually the CP asymmetries. And that's sort of the amazing, outstanding thing that actually the last, I would say, gosh, it's been almost 20 years now since the B factories first switched on to sort of look at this system and notice this unitary triangle, as we said, was basically going from B to D sort of transition, so the BD meson system. And trying to verify this, and in particular measuring some of these angles, has been a huge part of that program over 20 years. And so far, everything's looking very strong, although there's some anomalies here and there that we'll get to.
Another question, what exactly about the triangle tells us whether the Ckm matrix is unitary or not?
So the triangle, the condition for unitarity is really this condition right here, right? It's saying that because if I take either, V dagger V or VV dagger, I'm forgetting which one, and we look at the off diagonal, unitary says that those off diagonal entries should be 0. So these things have to sum to a 0 value. If they don't, then what that would mean in practice is that if we tried to draw a triangle, maybe the triangle doesn't close. Okay. So that's the unitary triangle picture. And what you want are many different measurements because, as I said, in the standard model, it's just one phase parameter, just the delta CKM, in other words, just the Yarlskog invariant. There's only one measure of CP violation that's going to enter here. And so it's going to have to result in all sorts of different predictions for various processes. They have to be correlated. And those correlations are encoded by this relation.
And one other question, sorry, I'm doing them out of order because I'm kind of trying to follow themes.
Sure.
Is the unitarity of the VCKM related to the unitarity limit in amplitudes? And I'm not entirely sure what is being asked. We might need to unmute Pranjal.
Well, I guess not having seen the discussion about this unitarity limit and the amplitude, just remember that, as we well know, in quantum physics, what we need to have are unitary transformations to basically preserve probabilities, right? So I think to the extent that that's the case here, we have to, we take, when we diagonalize our mass matrices for the quarks and leptons here, it's the quark ones that are relevant. When we diagonalize them, we want to diagonalize them via unitary transformations. Okay, so the reason for that is because then unitary transformations are going to preserve the appropriate probabilities, if you will. So kinetic terms are invariant under such combinations. So unitarity is just a general theme, right? If we did not have a unitary transformation going from the gauge to the mass eigenstates, what it would be sort of telling us is somehow we're missing some sort of degree of freedom or something like that. Yeah. So I'd say they'd be related in a sort of a broad sense. Right.
Does that kind of capture what you were asking?
Yeah, that was around what I was asking. Thank you.
Okay, good. Yeah.
Very good. Yeah. Great. I think that looks like all of the questions up till now.
Okay, excellent.
Great. So I want to say thank you very, very much to Lisa for this really fascinating talk. The first of three, I think three, maybe four.
Four.
I should check. Four. Okay,
Four.
sorry. This is just me not having checked. Okay, lately.